Hello everyone. So today in this lecture we will see the practical aspects of principal component analysis, and we would first use the classic dataset that people have been using over many years in multivariate analysis as well as nowadays in machine learning. Okay, so the dataset is this iris dataset. So iris is a type of flower and there are three species: Setosa, versicolor and virginica. You can see the pictures of three species here and try to see the differences. For example, here these petals are smaller, whereas here these petals are quite big. So these are three different species. This seems to be comparatively much more different than the other two, whereas these two seem slightly similar. Okay, so what we have is data on 150 flowers, 50 from each of these three species. And what are the variables? Sepal length, sepal width, petal length and petal width. So for every flower these four things are recorded: sepal length, sepal width, petal width, and we have such data on 150 flowers. And what we will try to do is, we will try to see which of these four variables are important in terms of variation, and we'll try to see, can we try to identify these groups of, these species, three species, using these four variables, okay, via principal component analysis. So let me go to MINITAB. I have pasted this data set in the worksheet. We go to Stat and we go to principal components. So these four variables we will select. Number of components to compute. Right now let us say 4. Okay, now this is an important point, whether we want to use correlation matrix or covariance matrix. When we studied correlation and covariance, we have seen that correlation is independent of units, whereas covariance changes with units. Okay, so generally whenever you have a new data set, what you do is, if all your variables are measured in same units, you go for covariance matrix. Okay, whereas if some of your variables are measured in different units, you go for correlation, so that standardization can be done and the quantity would become unitless. Let me explain further. So in this iris dataset, I have sepal length, sepal width, petal width, and everything is measured in centimeters. So when I say my PC1 consists of, say, L1 times sepal length plus L2 times sepal width, it makes sense because everything is in centimeters, so it can be added. However, in the earlier example that we had in the theory lecture for PCA, if you record, say, age, height, weight, blood pressure of a person, saying that PC1 is L1 times age plus L2 times BP doesn't really make sense because you are adding years to pressure. Okay, so in such scenarios you should go for correlation matrix because their quantities would be standardized and hence there won't be any unit involved. Okay, so right now because I am in the iris data where everything is in same unit, I go for covariance matrix. Which graphs we want? We want scree plot, score plot. Okay, we can also see biplot. I'll explain what biplot does, and then maybe loading plot. Okay, so let me click OK and we'll see what we get. Okay, we'll go to the graphs a bit later. First, let us see what are the things in the output that we can see. So, okay, I don't know if this is visible, so let me increase the font size. Okay, so these are some of the important things. So first, eigen analysis. So we got the eigenvalues 4.2282, 0.2427, 0782, 0238. Okay. And then proportion of variation explained by these eigenvalues. This is individual proportion, this is cumulative. So how do I compute this? 4.2282 divided by sum of these four eigenvalues would give me 0.925. Similarly 0.2427 divided by sum of all these four would give me 0.053. Okay, and if I add these two both, 4.2282 plus 0.2427 divided by sum of all four, I get 0.978. Okay, so first PC itself explains 92.5% variation. Okay, if I want to express in percentage, I'll have to multiply this by 100. So first PC itself explains 92.5% variation in the data. 2 PCs explain 97.8% variation. 3 PCs explain 99.5% variation. And overall 4 PCs explain entire 100% variation. Okay, so ideally even 1 PC would be enough. Okay, at most 2, not more than 2. Now how do I see which variables are important? So these are eigenvectors. Okay, so PC1 they have written. So actually equation for PC1 would be 0.361 times sepal length minus 0.085 times sepal width plus 0.857 times petal length plus 0.358 times petal width. So we can see here petal length is more important, most important, because it has highest coefficient. If you go to second PC, then sepal width and actually up to some extent sepal length are important. So the most important variables out of these 4 is petal length. Okay. Now we'll go to the plots. So let me first go to the scree plot. So you can see here 2, 3, 4. So this line joining second, third and fourth point is almost parallel to x-axis. So I would say here we have an elbow and hence only first PC is enough. Only one PC is enough, because after elbow, from elbow, everything else is equally important. So here they are equally unimportant. So only first PC is important. And that's what is told by our earlier picture also. 92% variation is explained by first PC itself. Now let me go to score plot. Okay. You remember how we compute scores? We use those equations that we discussed just now, put in values corresponding to every observation and get this. Okay. Of course, for correlation based PCA, you will have to first standardize your variables and then use them to get the scores. So here let me try to indicate species by different colors. So how do I do that? Let me show you again. Choose any point in the score plot, double click it. So you will see edit symbols. Go to groups, species indicate groups, and okay. Now you can see setosa are denoted by blue dots, versicolor are denoted by these maroon squares, and virginica are denoted by green diamonds. Okay. Now you can see that setosa is clearly distinct from other two, and even in other two there is some mixture, no doubt, but otherwise there is more or less good separation. So these 4 physical parameters, these 4 measurements can definitely help us in distinguishing between the species. Okay. Now let me, how does it help us? This helps us in a sense. Suppose now I come up with a new flower, I can take measurement of this flower. I can measure sepal length, sepal width, petal length, petal width. But the problem is I don't know how to identify the species. So I will do this, I will compute these measurements. Using these measurements and the equation of PCs I have, I can compute value of PC1 and PC2. I will use the eigenvectors as coefficients and I will get values of PC1, PC2, and then I will plot that point. So if suppose that point ends up somewhere being here, so what does it mean? It means suppose PC1 value is say 3.1 and PC2 value is say minus 6.5, then that point is somewhere here. So what would it mean? It would mean that that flower is most likely to have come from setosa group because its point landed closest to the setosa group. Getting it? So this way PCA can be used for classification. So dimension reduction is one purpose of PCA, but it can be used for classification also using this. Are you following me? Okay. Now let us go to third graph, that is loading plot. Okay. Now what are the things that we interpret from this loading plot? First thing, you can see petal length has the largest line, we will say arrow, there is no arrowhead, so largest line segment. So the length of the line segment in this graph is actually proportional to the variation of that variance of that variable which is proportional to information content of that variable. So petal length has highest variance, hence it has largest length. Petal width has lowest variance, hence it has smallest length. Okay. You can compute variances of individual variables. Let me show you how to do that in MINITAB. So we go to stat, then basic statistics, display descriptive statistics, sepal length, or maybe we directly compute variance covariance matrix, that is better. So we go to stat, basic statistic, correlation matrix. So sepal length, sepal width, petal length, petal width, and select, and we will also compute variance covariance matrix. So covariance matrix, okay, you can see here variance of petal length is 3.11, whereas variance of all the others is small. Okay, hence petal length has highest longest arrow here. Okay, now petal width is almost on the petal length. Why? So again we'll go to the correlation structure. So correlation is here. So see, correlation between petal width and petal length is 0.963. Okay, we have to focus on first row in every entry, first entry in every pair. Second entry is p-value to indicate whether the correlation is significant or not. So correlation between petal width and petal length is almost 1, hence the two lines are overlapping. Okay. On the other hand, correlation between petal length and sepal width is negative. Petal width and sepal width is also negative. That's why the angle between petal length and sepal width is petal length and sepal width. Okay, it is certainly moderately high negative correlation, so the angle is obtuse. Okay, and similar things can be seen here in the biplot. See, petal length has highest length, and the direction of these lines indicate the larger values. So petal length is larger probably in these two species compared to setosa. Setosa is here. Setosa is to the opposite side where this petal length is written, right? So petal length is probably larger in these two species than setosa. On the other hand, sepal width is probably larger in setosa compared to these two species. Okay. Similarly, sepal length is probably larger in these two species than setosa. Let us try to see via descriptive statistics whether it is true. So descriptive statistics, we will have these 4 variables and we will compute by species, means for each species we will get mean and variance. So mean, we don't need everything else, so we will just compute mean, maybe median, minimum, maximum. Okay, variance also we have already seen, so we don't need it. Okay, see here, setosa petal length mean is very small. It is 1.46. Okay, whereas for other two species it is quite high. Okay, and on the other hand, for sepal width, setosa has higher values than other two species. Okay, that's what is indicated in biplot. Why the name biplot? Because it plots two things, variables as well as the observations. Okay. Again, angles in the biplot also indicate some sort of correlation. So positive correlation generally acute angle, negative correlation generally obtuse angle, and near zero correlation generally 90 degree or right angle. Okay. So these are some of the things that we can interpret from a biplot. So let me stop here. Thank you.